surface of underdog visco, or sorry, NaCCOC. And here's kind of a global picture. And somebody asked a question about orientation in checkerboard, and just by looking at this picture, you can see that in some region here, these lines are running in the x direction. In another region, they're running in the y direction. So as there's been a lot of discussion on nematicity here, I imagine, Steve's lecture. So there is, just even by looking at this picture, a nematic character to it. Some directions in x and some directions in y. So you can also ask the question, what are the size of the nematic domains? Okay. So the way, one way of doing that, so there's some unidirectional domain. And here's another later picture that I guess you created, perhaps. Is that right? Of the same thing. And so what you go, so you're going to know, roughly analyze which direction these are running. So the way they did it is you take this D form factor OX minus OY signal, and then you get 4 peaks. The x and y, you get a peak here, a peak here, peak here. This is OX minus OY, QY, and this is OX minus OY, that QX.
That's invisible out here.
Sorry?
That's invisible back here.
Okay. Turn the light on. So this is QX and QY. Take a Fourier transform of this on the oxygen and X and Y sides. And as I showed you earlier, you get peaks here and here. What you're measuring is the Fourier transform of OX of Q minus OY of Q. Then what you do is you put a mask here and do the inverse Fourier transform. So the question you're asking is which parts of the sample have a density wave in the y direction. And when you take the inverse of this, you're asking which parts of the sample have a density wave in the x direction. And in fact, what they plot is the difference of those two. So this is the thing that's actually plotted. And what this means is that in the orange region, the density wave runs in the y direction. In the blue region, this D form factor density wave runs in the x direction. And you can put the original picture back and you can confirm this with your own eyes that that's roughly what's happening. Anyway, so that's just to show you that this is the characteristic domain size of the nematic order. It seems to be larger than the charge density wave order, which is only about that much, and this seems to be at least twice as long. And so these domains form, and you can now measure the strength of the nematic autogram as a function of doping, and so on and so forth. So I'm not sure, a lot of the data is still under progress, but let me just show this schematic plot. Then the idea is that all of this disappears, both the nematic and this D form factor disappear on 19% doping. And now I want to think about the nature of that quantum critical point and how that determines the strange metal. So in fact, I'm going to just take a very simple model where I throw out everything except the nematic autoparameter and the Fermi surface. In reality, there's many more things to worry about, but let's just start with that. And that turns out to be a theory that many of us have studied for the last 20 years for different motivations, and work goes on, but we've understood quite a bit. I'll show you a kind of end with that. Okay? So that's the motivation. And as I've emphasized, it's plausible this is an important ingredient of what's going on in this actual strange metal, but it's almost certainly not the whole story. All right, so here's the model we're going to look at. And we're back to our quantum critical games. We start with a Fermi liquid, which has some Fermi surface, which has the full square lattice symmetry. Then we crank up some interaction, and I won't say what, just crank up some interaction. And because of the change in interaction, you have this Pomeranchuk instability. Who mentioned it? I think Andy or Pierce, remember? you have a Pomeranchuk instability to a Fermi surface that is distorted either in the x or the y direction.
You showed photo.
Sorry?
You showed photo on the rank.
Right. So now we can define an Ising autoparameter called phi, which is 0 in this and non-zero here. And you can see one way to define it would be to just take phi would be integral over k of c dagger k ck times cosine kx minus cosine ky. So if your Fermi surface looked like this, then you rotate by 90 degrees, this changes sign, so this would be 0 in this phase. If it looked like that, you have a positive value. If it looked like that, you have a negative value. So that's your Ising autoparameter. It has either positive or negative values, and you ask for quantum phase conditions where you have the onset of this autoparameter. And we're going to assume that there's a second order quantum phase condition and try to understand something about its structure. Okay, but before we do any calculation, let's just draw a few pictures that we can make very generally. So, as in my very first lecture where I talked about a quantum critical point and all the things that happen near it, I can, by just the same sort of arguments, draw this kind of finite temperature phase diagram. So what, here I'm ignoring everything except the Pomeranchuk instability. So what's going on here? So out here I have some coupling lambda. Here I have a Fermi liquid where phi is 0 and the Fermi surface is rectangular. And here I have the pneumatic state where the Fermi surface is square and rectangular here. And these are Fermi liquids. Very conventional Fermi liquids because they just have a Fermi surface that's sitting there. And the phi fluctuations, phi is a discrete symmetry, there's no Goldstone mode or anything. So phi fluctuations are completely regular, and these are just Fermi liquids. So there are two Fermi liquids. So we have a phase condition between two Fermi liquids, which involve this Ising autoparameter. Now, in fact, just like the discussion of the spin density antiferromagnetic Fermi liquid transition, there can be additional instabilities here, but I'm just going to ignore that for today's lecture. Now, one feature of this autoparameter phi is Ising. So once you go to finite temperature, so one very useful thing to know is once you're at finite temperature, then as far as which phase transition can occur and which can't, and how they respond to disorder, and so on, you can think classically. You can forget the fermions, because roughly speaking, the fermions always have a finite odd Matsubara frequency, so they never lead to any finite temperature singularities. So the only thing that's possible that can be important for long distance physics at finite temperature, the boson degrees of freedom, and that's just an Ising autoparameter. So at finite temperature, you expect there to be an Ising transition, and that Ising transition would be the same as in the universality as the Onsager solution of the 2D Ising model. You have the same critical exponents and so on. It's just a finite temperature Ising critical point. So that's this line over here. On the other hand, you cannot neglect the fermions at zero temperature. So you might guess, well, at zero temperature, at this critical point, you're not in 2 dimensions, but 2 + 1 dimensions, because it's space and time. And so this critical point has an Ising character with a 2 + 1 dimensional Ising model, like this one was 2-dimensional Ising model. But by now, hopefully, you've learned enough to immediately recognize that can't possibly be true, so that's not correct. But instead, what you have is a non-Fermi liquid state, which I will say more about. Now, similar analysis can also be done for the spin density wave critical point, but this is a little bit simpler, which is why I'm looking at it. And finally, then there's this quantum critical region above, as always, as in my first lecture, and that perhaps I should put a question mark, has something to do with the strange metal that's in so many compounds. But we want to understand this strange metal, at least in this theory. Yeah.
Is there an upper temperature scale that
Sure.
says that, no?
Yeah, sure, absolutely. There should be some upper bound here, which I haven't found. Beyond which you can't use this continuum theory. But let's just say I want to understand what's happening down at OT for now. Yeah.
Strained metal is a special kind of non-Fermi liquid. It's marginal. How do you know that?
What do you mean it's marginal?
I mean the self-energy scales as energy itself. An exponent is 1.
It's the marginal Fermi liquid.
How do you know that? From which experiment?
When resistivity and scales with temperature.
Resistivity is not self-energy.
Oh, okay, I thought it's.
There are certainly claims like that. Resistivity is linear temperature, yes. That doesn't tell you anything about the electronic circuit.
At least the opposite is true. I mean, when you have self-energy scaling
in certain uncontrolled phenomenological models, such claims have been made. They're generally not true. They're not true of any model I've looked at. Yeah.
So we heard from Senchel previously that this strange metal phenomenology goes to such high energy scales like 1 eV and such low temperatures like 10 Kelvin that, quote, it can't possibly arise from Fermi surface coupled to critical boson. Do you have a comment on that?
Well, I would be happy to just explain what happens down here. Okay, let me say that's my limited aim. What happens at higher temperature, there's some complicated crossover, I don't know. I don't think, 1 eV, I don't know why I talk about 1 eV, but it's also incontrovertible in the pnictide and many of the other compounds. The strained metal is explicitly associated with the quantum critical. It appears where there's a quantum critical point, it disappears away from it. There's beautiful data using Matsuda probably show of that type. So there's certainly many compounds where there's a clear connection, even in the phase diagram, between the strained metal and the quantum critical point. Now, for the cuprates, I haven't made any claims, but maybe there could be a phase with some gapless excitation at low temperature, with Gates theories and so on. I think that's Sentel's favorite model, but there's absolutely no evidence for any of that physics in the actual experiments. So, yeah, is what I would say. Patience. So just wait and see who's right. Certainly a lot of fantasy has been coming out of MIT that made no sense. This is being recorded. I don't care. All right. So let's actually write down the theory for this quantum critical point. So we're going to follow the same strategy that we followed for the antiferromagnetism. So we have an autoparameter. We write down the usual bosonic autoparameter for the quantum critical point. In this case, it's an Ising variable, so there's no vector, but other than that, it's the same bifold field theory. And then you have the Fermi surface, which is shown here with some dispersion and some round shape. And then finally, we have to couple them together. Now, for the antiferromagnetism, the coupling was, led to hotspots and all of this stuff. Here, in some ways it's simpler, in some ways more complicated. But we can at least figure out what the coupling is. And in fact, it's important almost everywhere around the Fermi surface. So there's no real hotspots. There are certain cold spots, which I will just ignore. But almost the entire Fermi surface is hot. And the reason for that is, this coupling between phi, the definition of the autoparameter, it seems to involve electrons with all momentum. So you just couple them together this way, you take your autoparameter phi, and you have them coupled to the electron in exactly the way you define the autoparameter. And this has all the right symmetries of the autoparameter and of the electrons. So now if you look at this form factor here, you see that this vanishes along the diagonals, but away from the diagonal it's non-zero. And so really every point on the Fermi surface scatters this phi very, very strongly. So that's both good and bad. It's good because now you don't have to focus on one particular point, but it's bad because you have to worry about every point, and then you don't know quite how to take the low energy limit. All right, on a field theory, which involves every point in the Fermi surface. Okay. All right, so that's the model, and now we have to figure out, now go beyond perturbation theory, beyond just simple Hartree Fock. What can we say? So here's a coupling G, and let's just go through now a little more completely what happens in powers of G to some G squared ordering. Let's see what we get.
What's the index alpha is for?
Alpha spin, and again, there's no role. We can ignore alpha completely. Yeah. All right, so this is the key point, which comes out of when you look at the structure of the perturbation theory a little bit. So what's happening here? If I look at this coupling, phi, just imagine phi is very, very long, q is really small. That's the long wavelength phi fluctuation. Now that's going to scatter the fermions, and let's look at how they scatter the fermions around on the Fermi surface. Let me pick a point here on the Fermi surface at point k naught. So, and here's Q. Okay. Now if Q is pointing in this direction, it will scatter the electron from here to there. And that's cleverly chosen to be tangent to the Fermi surface. Now if an electron moves tangent to the Fermi surface, its energy doesn't change. On the other hand, if Q was pointing in this direction, it will get scattered this way, and that energy will change linearly in Q, which is perpendicular to the Fermi surface. So if I have an autoparameter pointed in this direction, then an electron here will get scattered transverse to the Fermi surface. Electron here will get scattered parallel to the Fermi surface. The electron here will also get scattered parallel to the Fermi surface. So if I take an autoparameter in this direction Q and ask where on the Fermi surface is the electron scattered parallel, so that you have very low energy transfer. That only happens at 2 points, k naught and minus k naught. Everywhere else it's scattered transverse to the Fermi surface. And those it's parallel to the Fermi surface. So that suggests, even though there are no hot spots, if for a wave vector fluctuation along this direction, you expand about k naught and minus k naught. You take your fermions and you expand them about this point. So you take your fermion kinetic energy about this point and about that point, and you expand it at x and y. So you're going to get something that looks like a hotspot but isn't really, because there's nothing special about that point. It just happens to be the point that's picked out when the autoparameter has a fluctuation in this direction. Okay, so what does that look like? So my energy, here's my Fermi surface. So E of k, that's the dispersion. So E of k, some function E of k. So let's just take E of k is kx squared plus ky squared over 2m minus mu. Okay. So let me pick some point k naught. So let's take k naught is equal to kf 0. And in this case with the mu, since the energy must vanish at that point, so that tells me that kf squared over 2m is equal to mu. So then what is E of k naught plus q? So you do this expansion now, you plug this in here and you expand, and what you'll find, and this is equal to, again, factors of 2, I may not get right, it will be some kf over m times qx plus k plus I think qy squared over 2m. So what you see that the dispersion is linear in this direction, in the x direction, and quadratic in the y direction, about that point. Okay. So therefore I have a fermion here I call psi plus, and a fermion here I call psi minus, and this is the theory then. So the fermion psi plus has a dispersion linear in x and quadratic in y. And psi minus is exactly the same, except the x direction changes sign. The dispersion, whole like here, particle like here. Then this Yukawa coupling that I wrote on before just becomes this very, looks like a Yukawa coupling. And phi is dispersing in the y direction, so it's just d by y phi squared. You can add a d by dx, dx phi squared, but it makes no difference, it's irrelevant. So this is the theory then, now written as a field theory. So this is a very simple field theory, even simpler than the hotspot theory I wrote earlier. It involves two species of fermions with this strange anisotropic dispersion, which is linear in one and quadratic in the other. And then there's ordinary Yukawa couplings. And gradient in terms of phi, you can add as many derivatives you want in all directions. This is the only one that matters in the end.
Question?
Yeah.
So this is a different type of dispersion than we're used to. Usually we think of dispersion of the band structure K.
Yeah.
And here it's in Q, which is a momentum transfer.
No, no. We just pick, the only thing I've done is I've picked this point and expanded about that point. That's all. You pick your favorite point on the Fermi surface and you expand about it. You'll always find that it's linear transfers to the Fermi surface and quadratic tangent to the Fermi surface. It's true for any Fermi surface at any point, unless there's some cusp or random singularity or something.
Okay, so K is 0.
What?
Q is 0 means you are on the Fermi surface.
Yes. Yeah. Because you pick any Fermi surface, generic, pick any point, and define Q as a deviation from that point. You'll find that the dispersion is linear in one direction and quadratic in the other.
So this is just linearizing the dispersion, but keeping the next term as well. Linearizing the correct.
You're keeping the leading term in both directions. I do throw out a kx squared term,
Yeah.
because it's not a kx. Yeah, Costa.
So if you consider a particular fluctuation of the boson field with the momentum q,
Yeah.
as you argue, it's like 2 points.
Yes.
But if you consider different fluctuations, like different points.
Yes. Yes.
You sum this overall, also even for n.
Yes. So there's a long discussion of all this in our paper. In the end, really, we're going to this phi is going to have both qx and qy. It will have all directions. So really, we imagine at some energy scale splitting the Fermi surface apart into different patches. And the patches really are distinct theories. But you could say, if I have a fermion sitting here, right now this fermion here belongs to this patch. But this fermion here also belongs to another patch over there. So which patch does it belong? Well, anyway, so if you look carefully at the structure of this theory, there's a hidden symmetry in this theory, which is analogous to Galilean invariance, but in space and time, in x and y. And that guarantees that you get the same answer independent of which patch you think you're on. But there's kind of a sliding symmetry of the theory, which guarantees that nothing depends on which point you expand about. You can read our paper for more about that. But there is this theory has a symmetry, which is related to the fact that if I think of this x as time and y as space, this combination has a Galilean invariance. Because of that, it turns out it doesn't matter which point you expand about. Yeah.
Maybe I'm missing something like there's only gradient phi in the y direction.
Okay, then you can add a gradient x phi squared. It just turns out to be irrelevant. So we're going to let's just do this now. Right? I'm going to do this later. Do it now. So we're going to do some RG analysis. So in RG analysis for the fermion dispersion, you're going to, let's say we x to x over s, where s is going to be e to the L of the RG scale. Then you see that to keep this dispersion invariant, you have to scale y going to y over s squared. To keep this thing, sorry, it's the other way around, isn't it? X, let's go to y squared. Yeah. So then this combination remains the same. So because of that, now you find if you add a term here which is d by dx phi squared, it will have twice the scaling dimension of this, so it's just irrelevant. So, you know. Anyway, so for now, you may not buy all these approximations, but let me just say I picked a point, and I've done this expansion about the 2 points. Now let me just do perturbation theory in this thing. And what you find when you do perturbation theory, you get answers that are fully consistent, in fact, numerically exactly the same as you would get by working with the full Fermi surface, with much less work, because you've already seen all the necessary approximations. Yeah.
What happened to phi squared and phi over 4?
So phi squared are tuned to be at a critical point,
Okay.
and phi 4 will in the end be irrelevant, at least in this 1 over n expansion.
Okay. I mean, doesn't the critical point, the coefficient of phi squared,
Yeah.
shift due to the power coupling?
Yeah, so you have to tune it to be at the critical point. Yeah. But there's still, it turns out the phi squared coupling doesn't renormalize. And because of that, the value of the exponent nu and the value of the exponent z are exactly related to each other. Again, these are details you can read in my notes or papers. But for now, let me just take this theory. All I've done is this expansion about the 2 points and do perturbation theory in G. All right, so the first thing you do is evaluate Landau damping. This is exactly the analog of the calculation we did for the hotspots. Okay, you just do this integral, and this is the answer. And sure, you know, if you go and open your Federn-Valetzka and do this whole calculation using the full song and dance of the Linhart function, the whole Fermi surface, you take omega and q, you get exactly the same answer with the same factor 1.45. So the patch theory really is many things exactly, and also makes the structure of the theory very clear. Next, okay, so this is what I did before. But now we want to look at the effect on the fermions. This is something I didn't do for the antiferromagnetism because it's just a little more complicated. So now let's do it here. So we do the perturbation theory in G and look at the self-energy of the electron. This is, you know, very much what we do in QED. This is the vacuum polarization graph in QED of the photon, and this is the electron self-energy. One difference from QED is that when you take this phi propagator, you don't take the bare propagator, but you take the normalized propagator, including the Landau damping term right here. Anyway, so you go ahead and do this integral, and what you get is that the self-energy of the electron goes at omega to the 2/3, and d over 3 is general dimension d. Okay, so this, I guess, is all resulting from Patrick Lee, I think, first, in very different context of gauge fields, but it also is here, this thematic point. Okay, so this is, you know, very exciting because if you're interested in non-Fermi liquids, because this is something that's much, much stronger than what you would get for a Fermi liquid where you get omega squared. Here it's omega to 2/3. Here I'm also assumed by dropping the phi squared term that I'm exactly at the critical point. Yeah.
Technical question. What is the reason that in any calculations we always include Landau damping in the bosonic propagator? Is it to kill some divergence?
Well, it's because that's what gives you the non-Fermi liquid behavior. We know that it is very important at low energies. If you didn't include it, you get a much weaker dependence. But on the other hand, if you went to next order in perturbation theory, you will find that you get less weaker. I mean, it becomes more singular. And every order in perturbation theory will become more and more singular, so that will tell you something's wrong with that perturbation theory. So on the other hand, if you do it this way, you get a very singular answer at leading order. And as I'm just going to argue at higher orders, you get a less singular, it doesn't get worse, it gets better. So that's good. So that means that you've really resummed the most singular terms.
So omega scaling.
Huh?
Because it scales linearly with omega.
In 3 dimensions, yes. So what I was going to argue in the next slide, so you work to leading order in G and you get omega linear omega. Then you work to next order, you might worry, maybe you'll get square root of omega. But you argue that in fact at higher orders, you never get a linear omega at all. It just remains, it's always omega, higher powers of omega. On the other hand, if you did what you had suggested, but I didn't put this in here, you would find it becomes more singular at every order. Yeah.
If I were to start with this electron self-energy,
Yeah.
and then calculate the boson self-energy based on that electron propagator,
Yes. Yeah.
would I still get lambda damping out?
You do, yes. At least at the up to 4 loops that's being controlled. 3 loops. Yes. Yes, you do. But we don't know it's true to all orders. Exactly. No, sorry. There is a scaling argument, so that's exactly. Yeah, that particular thing, to all orders. Yeah.
The coefficient doesn't change if you include only frequency dependent self-energy.
Yes, yeah, but it remains mod omega over Q. That follows from sort of an argument based on gauge invariance that the scaling dimension of phi has to be z minus 1. Okay. There is an argument of that kind, which is reviewed in the second edition of my book. Okay. So let me get to, so let me summarize. So I have a boson, I have a fermion. I just did some kind of conventional perturbation theory for the boson, and let me do this in d dimensions. For bosons, you'll find you get this q squared, that's this term here. This is now any direction tangent to the Fermi surface, it should be q parallel here, sorry. And omega over q parallel. So this is the Landau damping. For the fermions, you had the dispersion qx in one direction, qy squared in the other direction, and omega to the d over 3. Okay, so now if I look at these two expressions and I just compare, how do frequencies and momenta scale with each other? So with the boson, you find that momenta parallel to the Fermi surface squared, whereas omega to the 1 over, let's call it Z boson, where Z boson is 3/2. Okay. I get that right? Okay, I've screwed up somehow here. There's a little typo here, but okay, that gives me, if I take this literally, I get Z boson equals 3. But I'm talking about Z with respect to QX. So there should really be a 2 over there. Apologize, sorry. There's a factor of 2 that I just screwed up. It's a typo in this slide.
I guess that's good.
Huh?
Omega scales as Q per cubed, right?
There's a mistake here, but I will correct it in the online version of these slides. So, really, I should say 1 over 2 ZB over here. I would correct it on the board, but I'm not confident of my ability to get it right on the board, so I won't try. Anyway, the bottom line is if you look at how Q and omega scale with each other, for the bosons you get 3/2 in all dimensions. For fermions you get 3 over d. So this is the key point. Now the point is that Z fermion is less than Z boson for d greater than 2. What this means is that if I pick a given wave vector, and look at the energy, typical energy of the boson fluctuation, it's smaller than the energy of the fermion fluctuation, because Z boson is bigger than Zx. If omega goes as Q to the Z, if Q is fixed and Z becomes larger, omega goes smaller, or smaller Q. So the bosonic fluctuations are lower in energy at a given scale than the fermionic, typical fermionic fluctuation. So that's telling you the bosons are most singular. And that's exactly what Hertz said. Hertz said, forget the fermions, innovate about, focus on the bosons. Those are the most singular things. So what Hertz says is correct in 3 dimensions because of this. Because the Z's are different, the bosons are more singular. So 3 dimensions, basically the Hertz strategy is correct. Yeah. And he wasn't only thinking about 3, so he can rest easy. Yes. Those days nobody was talking about 2.
So,
yeah.
So in 3 dimensions, it looks like you get omega, the self-energy, fermion self-energy looks like It's proportional to log omega.
Yes.
So,
There's a log omega that appears.
but, so that's assuming a three-dimensional dispersion for both the bosons and for the free fermions and the free bosons.
Yes, yes.
What about, would this change if you artificially imagine that the electrons had a two-dimensional dispersion, a truly two-dimensional dispersion, but that the bosons had a 3D dispersion?
I don't know off my head why one could work it out. I don't know off my head. It would change, yeah. But so also this argument also shows that in some sense, this fermion self-energy correction, and in fact the coupling D is close to 0. So this means that I go to next order, I will get powers of omega that are higher than P over 3 for D equal to 3. So in fact the Leiden marginal Fermi liquid term is in a sense exact, apart from renormalization of static vertices. Yes?
So just want to confirm, so in your treatment, you still integrate fermion?
No, I don't think it. I'm just doing perturbation theory.
Sorry, yes, you start from the bosonic self-energy.
I'm working with this theory doing perturbation theory in G. That's what I'm doing. And now I'm giving a reasonability argument that from this I learned that if I was in 3 dimensions, it's okay to integrate out the fermions. Get almost everything correct.
And do you need to feed the electronic self-energy back to the, like, do you need to do it?
You can, I mean, it'll change some numbers, but it won't change the singularity.
So
Everything will
you just need to do it for one round.
That's it, yeah. If you want to get numbers, of course, it's very hard. But the point is that in 3 dimensions, if you by hand make G small, suppose your bare value of G is small, I'm pretty confident I can get actual numbers for the real theory. Yeah. Okay.
Well, just look at this. Even if you're in 2 dimensions, there's
Yeah.
some type here, but nevertheless, even if you're in 2 dimensions, Qx is still scaled as omega 2/3, while Q perpendicular scale is omega 1/3.
No, that's because of the typo. That's because of the typo. They both scale the same.
There's a reason why in D you neglect Qx.
No, there's a typo here. I shouldn't call this 1 over Z. Some people define ZD with respect to QY, some people define ZD with respect to QX.
All I'm saying
And I got confused between the two people in these 2 lines.
All I'm saying is that still, even in 2 dimensions, Qx and Q perpendicular have different scale. And this is the reason why you can't...
They're always a factor of 2 between them, correct?
Right, but this is the reason why in expression for D, you don't put full Q. You put only Q perpendicular.
Yes, yeah, but that's because...
Qx is much smaller.
Okay, okay, I guess I should get this right. All right, so the statement is that the way I should have defined it is Qx scaled as Qy squared,
Right.
scaled as omega to the 1 over Z. This is how I define Z. Okay. Now, the boson propagator, so if I have to compare this with this, so I should... everything is right. Everything is right. Thank you. Everything is right here. And this gives 3 halves. It's correct. Everything is correct.
Right, and at the same time, Qx is much smaller than Qy.
Yeah, everything is correct. So Qx, I don't think it makes sense to say Qx is much smaller than Qy, because you only have to compare apples with apples. You can compare energies with energies for a given Qx and a given Q. You cannot compare Qx and Qy. They scale differently.
It's the expression for D. Where you
Yeah.
generally put...
Yeah, so you should always compare Qx with Q squared.
D.
Yeah, here.
This one.
There's Qy doesn't appear here. It only depends on the curve.
Well, J depends on what Q.
Right, but because Qx is much smaller than you're
That's what
right.
I'm
That's why
saying.
you screw it up here. Everything is correct. Thank you. Yes.
Can you repeat what, since the fermions have high energy, the perturbation theory is okay?
Well, because the energy denominators are larger. So all the energy denominator of the bosons will be smaller than the energy denominator of the fermions.
So regardless of the value of the coupling.
Yeah, so I mean, what we're worried of, so we want, so when we're doing perturbation theory, first of all, we have to assume the coupling is small. If the coupling is not small, all hope is lost. But even if the coupling is small, we have to worry about the fact that the energy denominators will blow up on us. And that's what happens in 2 dimensions. No matter how small the coupling, energy denominators blow up because they all scale the same way. But in 3 dimensions, some of the energy denominators are larger than the others. So we throw those terms out because the coupling, small coupling takes care of them. Okay, so then what are the terms that are left over, which are small energy denominators? Those are exactly the terms in Hertz's theory. So we're okay. This is getting very technical.
In the water phase, this is the critical point.
Is that the critical point? Okay, so the point is that in 2 dimensions, which is what we're interested in, there's a special resonance that fermionic and bosonic self-energy scale exactly the same way. They resonate with each other, and you can't prefer one over the other. They're strongly coupled to each other. And so you have a much more complicated problem to worry about. There is, you have to try various small parameters, and people have tried various things, and we think we have some general understanding of the structure of this theory, but I believe that much of the structure that I write on is basically correct. There are certain extra exponents that appear, which I won't go into right now. But let me conclude this discussion by, suppose I didn't know any of this and somebody gave me this theory. How could I have seen that this theory has z equals 3 halves? The whole argument for 3 halves just came from Landau damping, and some people don't like that because you're integrating at all degrees of freedom, it's not dangerous, and so on and so forth. So here's a quick way of seeing it without doing any calculation. The only thing I assume is that whatever fixed point this theory flows to, that fixed point is some kind of non-Fermi liquid. And if it's a non-Fermi liquid, what that means is the self-energy has a power of omega, which is rather small. And certainly it would mean that this line, let's assume we can ignore the linear time derivative. Suppose we can ignore this one. It becomes irrelevant. Now that we take this theory, just do a rescaling. So here's what I do. I rescale x by x, x over s, y by s over 1/2, that's what I had before. And then tau by tau s over z. So normally you fix z by saying these two must scale together. But since this term is gone, I haven't fixed z at all. But I go ahead and I take this rescale in, and I rescale every term. I find this is invariant, provided I choose phi and psi to scale this way. Just a simple exercise, a power computation. And then G will scale this way. And now you see that G becomes invariant, reaches a fixed point if Z is 3 halves. So effectively the coupling reaches some universal value in this way of thinking, or if there's some universal fixed point structure. And that fixed point, at least at tree level, must have 3 halves. So if there's a non-Fermi liquid fixed point, the simple argument tells you Z must be 3 halves. Now, it doesn't rule out that there are some higher multi-loop corrections that change this value of Z, but so far nobody's ever found a graph that changes this. It probably is exact, but there's no proof of that. There's another problem which was considered by Sachdev, where he throws out the psi plus and only keeps the psi minus. And that would be valid if you break time reversal. So suppose you have a chiral metal which has only one-sided Fermi surface. And then for that, Sachdev has proven all of this is exact. Basically, these 3 halves exact. There's a non-Fermi liquid. That's probably the only well-established, rigorous non-Fermi liquid we know today in 2 dimensions.
Sorry, don't you need to break conversion symmetry as well throughout psi plus?
Okay, and the time reversal will also be very important. Depends, if you have no spin orbit, inversion and time reversal are pretty much the same.
Sorry, does this scaling argument carry, this is meant for the case of d equals 2?
Yes.
This argument there.
Yeah, so it doesn't work for d equals, well, there's lots of subtleties for d equals 3, it doesn't work there. For one reason, you don't just get 2 patches, you can get an infinite line of patches for a given direction of Q. So the whole patch construction doesn't work either. All right, so to summarize, and here's like the summary of a Fermi liquid. So Fermi liquid we know is a state of matter, which is a metal with a Fermi surface. The volume of the Fermi surface obeys the Levin duration. There are low-lying quasi-particle excitations, which are infinitely sharp near the Fermi level, and their energy scales linearly with Q. So if you think in that language, you would say Z is 1. The specific heat or the entropy density of a Fermi liquid is linear in temperature, and here I've written linear in temperature in the world's most complicated way, theta equals D minus 1. This is just for other purposes. I should have changed that for this slide. And the entanglement entropy of a Fermi liquid goes as the area, it violates the area log as an area log area with the volume of the Fermi surface up front. So for this non-Fermi liquid in the nematic critical point, what do we find? So first of all, there is still a Fermi surface. The Fermi surface doesn't disappear. And one way to define the Fermi surface is, for example, measure n of k, the number of particles in momentum k. In a Fermi liquid that has a discontinuity at kf, now it has a singularity at kf. And that singularity is determined by these exponent z and other exponent eta that I haven't talked about. But there's still a Fermi surface, and it also obeys the Levin criteria. So that doesn't disappear. But what is changed is that these sharp excitations in the Fermi surface become diffuse, and the energy as a function of distance from the Fermi surface goes as q to the 3/2. So that's the basic property. And if I use this formula and put z equals 3/2, then the specific heat goes as T to the 2/3, and the entanglement entropy is believed to have the same log logarithm. So that's a summary of what I've talked about so far. Okay, so what I've discussed then is our current understanding of this point, of the nematic quantum critical point in 2 dimensions. It's a non-Fermi liquid of a very interesting type, and in some cases, really in some way, the only non-Fermi liquid for which we have a reliable theory. All right, so let me just very quickly, I'm sure you're tired of hearing from me, just say a few things about the strange metal. Now, what about its finite temperature? So again, this is a problem that's been looked at by many people, and there's a long list of papers, and I'll review the basic argument briefly, that the resistance in this region goes as T to the 4/3. And I believe that argument is basically incorrect. And this was pointed out especially in these papers by Maslov and Chubukov. And it has to do with the fact that the arguments, that the computations ignore constraints from total momentum or effects that are sometimes called drag. So let me try to explain what this is, and then I'll conclude. So we've been thinking a lot about what the transport property of this metal is. Really is. It's not T to the 4/3. But it's still a subtle question, and it seems to depend a lot upon exactly what's happening in the details of the system. So unlike electron self-energy, resistivity is a very subtle thing, much harder to properly understand. Okay, what's the idea? So now, suppose we have quasi-particles. Suppose we have a Fermi liquid. How do we compute resistivity? Well, there is a standard rule that you can read up in Simon's book, or the Boltzmann view. Says, okay, if you have a Fermi liquid, you identify the charge carriers. These are electrons or holes that live near the Fermi surface. Just figure out their scattering matrix of impurities or of phonons or whatever. And then once you figure out the scattering rate, you figure out how much the current gets degraded, and that gives you the resistivity. So that's a standard textbook Boltzmann calculation. Now, if you carry that out for electron-phonon scattering, you would get Bloch's law, which is T to the 5th. Okay, so this goes back to 1932 or something. It is Bloch. Soon after the discovery of quantum mechanics, predicted the resistance of metals at low enough temperatures, it goes T to the 5th. Okay. Now, if I do the same argument for the nematic quantum critical point, go through the same calculation. I don't really have quasi-particles, but let me just ignore that. Let me just do the same kind of scattering analysis of these Green's functions. Put it in some quasi-Boltzmann equation and see what I get. You will get Q to the 4/3. So that's the answer. However, there is a famous objection to Bloch's law, T to the fifth, which actually you can already find in Ashcroft and Mermin. So here's my beat up copy of Ashcroft and Mermin, and I looked it up, and there's a little footnote saying Peierls in 1932 pointed out that actually Bloch's law is probably not correct, and the resistance is even smaller than T to the fifth. And this effect is sometimes called photon drag. But if you look at the next sentence in Ashcroft and Mermin, it says, but this behavior is not yet observed, has yet to be observed. Now we couldn't have to change that because I understand Andy McKinsey has really a new experiment where he actually sees this effect, the Peierls created in 1932. But for this reason, so this was kind of forgotten, and people have just assumed that Bloch's law is correct, and it does seem to work in real life. So who knows what Peierls is worrying about? So you have to apparently take a really pure crystal to see deviations from Bloch's law. So let me try to explain what Peierls is worried about. So now we have two systems. In a crystal, you have electrons and you have phonons. And they're scattering of each other. And there's no long wavelength scattering. So the lattice, reciprocal lattice vector doesn't play any role at all. So the momentum is conserved in every scattering process. So as they scatter off each other, the electrons, they're slowly scattering, this is weak coupling, they're exchanging momentum with each other. So the total momentum of the electron-phonon system is conserved. So if I put a battery on the system and I set up a current, I set up an electric current, those electrons will eventually scatter off the phonons, and the phonons will take some of the momentum of the electrons. But wait long enough, the phonons will give the momentum back to the electrons. So I'll get some optimal thermal state, which will have the same momentum as the initial current carrying state. May have a slightly different current, but the current will always remain non-zero. Because there's no way, at least it's very, very hard to find a state which has finite momentum and zero current. It's possible, but it's very, very rare. It's not entropically different. Momentum and current are of course two different things. The electrons carry momentum and current. The phonons only carry momentum. So in fact, if momentum is perfectly conserved, it doesn't matter at that point. The resistance is zero. The current will flow forever. On the other hand, no crystal is really free of defects. There's always something. And so in practice, what happens, the phonons are very long wavelength optics, and they eventually hit the boundary of the crystal, or they hit dislocations and other impurities. And this is quite fast, and they quickly lose their momentum. So because this is so fast, Peierls, you don't have to worry about what Peierls was saying. The electrons give their momentum to the phonons, and they can just pretty much say bye-bye to that momentum. It will never come back. It very quickly disappears somewhere else. So the relaxation due to defects is much faster in most crystals and most metals due to a phonon scattering of defects or non-linear phonon effects or various other things that are not fully understood than the electron-phonon scattering, which is relatively small. The coupling is weak. Okay. So that's basically the answer. That's why Bloch is correct, because the defects relaxation is fast enough, and you just need to worry about that relaxation process to get the resistivity. Okay, now let's take the same argument to the nematic critical point. Now the whole point of my discussion so far is this coupling is very strong. It's not weak, it's very strong. Electrons are very quickly giving the momentum to the phi and back and forth. They're really the same object, really. They have the same Z and they're on resonance, very strongly coupled. So this is really the fastest thing that we have in the system. And this is much, there's also interpack scattering, which is slightly less fast, but also quite fast. So if I just take this system, it conserves total momentum, it's resistant to zero, period. It's not T to the fourth, it's zero. Because everything in this Pax theory, and in fact, you can also take a full Fermi surface theory and show that it must have zero resistance. So you have to have something else to give you resistance. And one of those, so in fact there are some defects maybe. Okay. So say there's some defects, we can act on the pneumatic bosons or they can act on the electrons. So we've estimated these rates, and that's why I'm going to just describe. It turns out this is the most important process. It's faster than this one, so that's where most of the momentum ends up. And so the resistivity, so here the bottom line is the resistivity of this non-Fermi liquid is not determined by the scattering rate of the quasi-particles. It is determined by how fast some bosonic autoparameter relaxes momentum on these things. Which is in fact, this bosonic autoparameter doesn't even carry charge. It's neutral. It's still at 270 to this day. So that's the point I want to make. So here's the actual calculations, and I'll stop. I'll just outline. So here's the theory I began with. Now let me just change the theory a little bit. Let me take this dispersion here, which is some band dispersion. Or let me just make it parabolic with some corrections. So I don't have any umfla. And also take the cosine here and expand it, which is pretty good for reasonable size Fermi surface. This theory has zero resistance. It's an exact statement. This theory has zero resistance because it has a conserved momentum, and this chi Jp not equal to 0 means that the most optimal state carrying current has a non-zero momentum. So the resistance is 0. And why it's called drag, one way to think about it, you set up a current, and the current drags a momentum. There's a cross susceptibility. Every time you have a current, you have a momentum. So to figure out what the resistance is, you've got to figure out how you lose the momentum, not how you lose the current. Because that's the thing that's stopping everything. That's the bottleneck. All right, so I guess I've already said this. So what's going to stop the momentum? So we've just looked at one process so far, and there's many others you could think about. And that just comes from this picture. So here's a picture of the pneumatic order that I showed you earlier. And what you can see is that there's some impurities that go else. Because locally, it's taking the pneumatic fluctuations, and one way they're pointing here, and one way the other way they're pointing here. So this is like a random field. This is an Ising autoparameter. Here the field is plus, and here the field is minus for the Ising rotation degrees here. So in the crystal, there's clearly perturbations that point in the two directions. So let's take our theory and add this random field to it, which is some Gaussian random field. You can also add a random potential, which other people have done, as I'll show in a minute. And then figure out the relaxation rate of the momentum and then the resistivity. There's actually a beautiful formalism called the memory function formalism, which again goes back to the 60s and 70s, but haven't had a peak of usage in many, but it's been forgotten, at least among quantum condensed matter theorists over the last 10 to 15 years, with the exception of Achim Roche and also, who's the guy right there, sorry, Nathan Andre, who have done some very beautiful work in one dimension using memory function formalism. So you can apply this to this patch theory here also, and compute the resistivity really quite simply due to both the random potential and random field. So first, for the random potential, we actually reproduce a bunch of other results in some ways much easier manner. Again, even in the clean limit, there was an important work of Zala, Naroki, and Alainer, and Paul et al. Here, who looked at the effect of random potential on various systems, both away and at the critical point, and we can reproduce all of that. But all of these papers didn't include this term, this H0. That turns out to be much more singular. And so it gives you various temperature-dependent resistivities, and we can only analyze it in the limit of very weak random field and high enough temperature so far, and we're of course trying to extend that. And I think so they turn out to be two interesting regimes. Roughly speaking, let me just say there's a high temperature regime where you ignore the Landau damping, where you assume that the bare kinetic energy of the Ising autogram is large, where in fact it's linear. And then a low temperature regime where it diverges is 1 over square root of T, where you have Landau damping taking over.
Excuse me,
Yeah.
question.
Yes.
How is your calculation different from the standard calculations of Joule activity and also the run correction states? Is there any extra small parameter, or is there any parameter?
Well, first of all, this is in many ways, but when applied to that regime, it reproduces the previous results. So that's sort of, so this calculation here, in fact, this calculation by Paul, Pepin, Arozzi, and Maslow is of exactly of the type you say, where they looked at the Archer-Aronoff corrections near the pneumatic critical point. And we can reproduce all of their results. But what they omitted was this particular term. They looked at this term. They didn't look at that term. But in general, both terms are present. So it agrees precisely with all of their results. In fact, we can extend it.
Just a perturbative calculation of Archer-Aronoff type, the only difference is that you allow the Zola acts on the bosonic field.
Well, in reality, once it acts on the fermionic field, it also acts on the bosonic field. But to really see that perturbatively, you're going to have to go high order perturbation field. They didn't go to high enough order to see that effect. It's much simpler to put it by hand to act on both. So this is a weak disorder limit, where the disorder is the weakest, the inelastic scattering is stronger. Now, in this paper, they also have results in the regime you're talking about. So you go, the disorder is much stronger, you go to the diffusive metal, and then you have interaction corrections there. But I'm looking here at much weaker disorder limit. It's in fact closer in spirit to this paper, which is also in the weak disorder limit.
It's a crossover. It's capture soul limits. It captures the crossover between.
That's right. So but they don't have any critical point there. They're looking at effect of short range interactions and Coulomb interactions on the Fermi liquid with weak and strong disorder. Right. That's the Zala-Dorothy line. So if you take their calculation and add in the effects of disorder, which is what was done here, I think only the strong disorder limit, if I remember right. No, they did it in both limits here. You get answers, and we can reproduce both of their answers, but in much simpler way. Yeah.
You said you're using memory function from this isn't. This looks like structure which.
Sorry.
This looks like a Kubo formula.
It's not a Kubo formula.
It's not a
Kubo formula. No, so it comes from the Morius one-thing formalism. It looks, it's very inelegant to us, and I think people have just been, the Kubo formula has turned out to be very powerful and useful for quasi-particle systems. But it turns out what we are realizing, partly from work in holography, is that the memory function formalism is actually better designed for non-quasi-particle systems.
I actually don't understand why is it a big deal whether you have quasi-particles here, because to calculate the Euler type connectivity, you can just insert the Green's function there. You don't care whether the self-energy part of the imaginary part of the self-energy part is large.
Okay, look, I agree. If you sum enough diagrams, you'll get the right answer. I agree with it. I agree with that. You sum enough diagrams, you get the right answer. But if you want to have some physical insight and get the answer at leading order and understand what's going on, then the memory function immediately gives the right answer in systems without quasi-particles. Whereas you have to work much harder in the Boltzmann-Kubo formulas. I mean, that's the only way I can reproduce, I agree. It requires a lot of mathematical sophistication to do what they do. And I'm very happy I can reproduce the answer for a few lines.
So essentially, what you showed in the next transparency was this behavior, is when H term is larger, right?
No, H term is very small.
So,
but then this crossover is, what we studied many years ago from Z equals 3 to Z equals 1. Okay, I haven't explained that, but let me just say quickly that if you imagine there's a regime which is a big if, there's a regime where Landau damping can be ignored, then you get linear resistivity. And then at low temperature you get a terminal. But anyway, so there are many other effects like this we're studying, but I think I will just leave this.
Do you need random Q for this?
For what?
If you go back to previous transparency, you have two terms.
Sorry.
Yeah, you have two terms in the first
Yeah, it is. So this is the random field term, and this is the...
Yeah, so suppose you neglect the second term with H.
Then the second term is not important. It doesn't give you any of that.
So you can just...
It's always much weaker in both regimes. You get kind of Fermi liquid-like effects at very high K. to get both the linear T at high T and the T to the minus 1/2, you need the random field. All right, so I think I've spoken enough, so thank you for listening. These are the 4 things I talked about. In my first lecture, I talked about onset of antiferromagnetism in an insulator and showed you a very satisfactory theory and experiments on triplons, spin waves, and Higgs excitations across the quantum critical point, which also agrees very nicely with experiments in tandem copper chloride. Then I reviewed the theory of onset of antiferromagnetism in metals. That leads to planar damping and D-wave superconductivity, as has long been understood. And then today, this morning, I talked about the idea that the critical theory has an extra symmetry that led us to think about the possibility of non-trivial form factors in a very particular way in the cuprate superconductors. And I think there's very convincing evidence from the cuprates, from the STM data, that there is such a D form factor present, and it's closely linked to the pseudogap. And so this form factor, if nothing else, seems to be a very powerful tool for enhancing the signal-to-noise ratio of just pulling out the autoparameter of the pseudogap. Whether it's related to antiferromagnetism, I think is plausible, but the antiferromagnetic theory doesn't quite get everything right, including the wave vector. Mainly the wave vector, I would say. And then this last lecture, I gave you a current status of the still evolving story of the simplest non-Fermi liquid we have. And it still goes on, and we are still trying to understand its instability, and hopefully we will get closer to experiments someday. So, thank you.
Are there any immediate questions? Well, if not, thanks very much. Thank you.